In this lesson, we're going to talk to those of you that perhaps are on the fence about whether or not to commit to purchasing a full version of the vCRASH 3 product. Of course, the vCRASH trial version is given out for free if you simply register at vcrashusa.com. You'll receive a link that you can use to download the trial version. We use the freemium model, as it's called. We give you a nearly fully functional trial version, but of course we're not giving away all of its functionality for free. And once you purchase the full version, you receive a USB key that unlocks all of the functionality of the vCRASH 3 product. So in this lesson, we're going to stage a collision without regard to rotation. This will be an example that you can construct on your own with your own trial version of vCRASH 3, and you can see that the results are exactly as one would expect based on the laws of physics and the rigid body dynamics model that's used in the vCRASH system. So first we're going to get a couple of vehicles, and of course all the vehicles are the same in the trial version. So here we have our two vehicles, and we can look at their mass properties, and we can see that they're identical, and in the trial version of the software, the mass, moments of inertia, and other parameters are locked, and the user's prevented from changing them. So, what can we do? Well, I encourage you to remain skeptical about any computer simulation model before you've put it through its paces. And you should make sure that you're comfortable with the performance and that you understand everything that the simulation's doing if you're going to use it. So let's set up a simple collision between our two identical vehicles. I'm just going to rotate this one to be at 90 degrees. Let's change the colors. You can see not all the features are locked. There are plenty of things you could play around with even in the trial version. So here we have a top-down view. Let's give this guy an initial speed of 10 miles per hour. And we can construct an impact where the principal direction of force, or the impulse vector, points through the centers of gravity, so there's no rotation. But we can also see that the tire force model is quickly decelerating the blue vehicle to rest, and via the contact model, it's also effectively decelerating and reversing the orange vehicle. Now we can get an idea of what the post-impact motion might look like by somewhat disabling the tire forces on both vehicles, and we can do this by setting the adhesion values for both vehicles as close to zero as we can. vCRASH allows you to set the adhesion values as low as 0.001, not quite zero. And if you go to your calculator and type in 0.001 times g, you'll see that's equivalent to a deceleration rate of 0.022 miles per hour per second. So it's not quite zero, but it allows you, by setting the adhesion value low for this in this problem, it allows you to get an idea of what the post-impact motion would look like on a frictionless surface, and that's sort of the ideal case we want to use to do a comparison between what vCRASH is doing and what our expectations are based on a typical ideal model. Of course, vCRASH uses an impulse model where the assumption is that all of the momentum is transferred instantaneously from one object to another. So in reality, we can access the post-impact velocities, and whether or not there are tire forces wouldn't matter to the results we would read off in the virtual crash system. And we'll do that in this demonstration. And now we can conduct some basic experiments to make sure we're comfortable with what the collision force model is doing. Is it doing the right thing? How do we know that the collision force model is satisfying the laws of physics and whatever our expectations are? So here we have two identical vehicles. The collision is such that there is no rotation, and so we can model this with a simple one-dimensional impact model. So let's go to our whiteboard. Let's say here's my x-axis. X hat. And let's say both of my vehicles are constrained, only allowed to move along this x-axis. So here's vehicle 1, here's vehicle 2. Physicists love representing objects as dots or spheres, so I'll continue with that tradition. And vehicle 1 is moving along the positive x direction. I could draw that a little better. Okay, vehicle 1 is traveling along the positive x-axis direction with an initial velocity, which I will call v1i for the initial velocity of vehicle 1. And let's say vehicle 2 is at rest. The closing speed, which I note as vreli to mean the relative velocity vector, the initial relative velocity vector. And here I'll define it as v1i minus v2i. Now this is a vector quantity, but since I've constrained or forced my masses to only move along the x-axis, I can do away with the vector notation and just treat these as scalar quantities. And so this, of course, is 0. And so my relative velocity, initial relative velocity, is simply equal to v1i. We also call the relative initial velocity the closing speed. In this case, this 1D case. Now, what do we expect for the final velocity of vehicle 2? We know, here's my x-axis, after impact, we expect both vehicles now to move together along the x-axis to the right. And of course I'm cheating, I already know they do that in our simulator. But here we want to show, using our traditional calculation methods and accident reconstruction, that there are no surprises in what the virtual crash collision model is doing. So let's go ahead and write an expression for what we expect vehicle 2's delta V to be. We know it's a positive quantity, and we know we can just write it as the product of the closing speed times 1 plus the coefficient of restitution all over 1 plus the ratio of vehicle 2's mass to vehicle 1's mass. Now in our trial version of the software, M1 is equal to M2. You're not allowed to change the vehicle weights. Sorry about that. And so this expression now just becomes the closing speed times 1 plus the coefficient of restitution all over 2. Why do I care? Well, now we can start to do some experiments and start to keep track of some results. What that means is that if I make a graph, those are not very good coordinate axes. Okay, if I make a graph of the closing speed in my simulation and delta V for vehicle 2, I should see a straight line in my data. And if I do linear regression fit, that fit should have a slope equal to, you guessed it, 1 plus whatever the coefficient of restitution is in my simulator, all divided by 2. And this is a nice cross-check to make sure that my simulator is doing what I expect. If I see that that's true, and I have a nice tight linear fit in my data, then I can have a lot more confidence that this thing is doing what I expect. It's doing the right thing, satisfying Newton's laws. And of course, delta V2 is simply vehicle 2's final velocity minus vehicle 2, the vehicle 2 initial velocity, which is equal to 0. So delta V2 is equal to V2F. So I can either make this graph using delta V2, or I could just keep track of V2F as a function of V real I, and I'll see the exact same linear, I should see the exact same linear fit with the same slope. Well, let's see what happens. We've got the theory, we know what to expect. Let's see if that's indeed what happens. Here I have my spreadsheet tool. I'm going to keep track of our results. Here I'll log our input. And let's just track it versus V2F, which is the same as delta V2. I'll show you that's true, that holds. So we'll start with let's start with a 5 mile per hour, and then go to 10, 20, 30, 40, 50, why not? So we'll simulate 6 data points and keep track of the results from the simulator. Let's move this aside. And we want to access the collision data for the event, and even the trial version allows you to gain access to that detailed information. You simply go to Auto EES, and this is basically a data container. It shows you all the properties of your collision. You can even change the collision parameters, and for this collision the most important parameter is going to be the coefficient of restitution, which vCRASH sets by default to 10%. We're not going to change that in this example. What we want to get is the post-impact speed for vehicle 2. And under object 1 and object 2, we see the pre and post-impact information and the delta V. So our orange vehicle is object 1 here, and we could see that its pre-impact speed is 5 miles per hour, which is what we set it to. And the post-impact speed is 2.279 miles per hour. The delta V then is 2.721 miles per hour. And if we go down to object 2, since the two vehicles have the same weight, since this is the trial version, you can't change that. I bet you by Newton's third law, there it is. Delta V for object 2 is exactly the same magnitude, 2.721 miles per hour. And the post-impact speed is, as I promised, exactly equal to its delta V for object 2, the blue car. So that is 2.721 miles per hour. So let's enter that post-impact speed into our spreadsheet, 2.721 miles per hour. And this is, again, the collision model assumes instantaneous momentum transfer. So the exact character of the impulse delivered to either vehicle is not taken into consideration, so the effect of tire forces is not considered during the momentum transfer event. So it didn't really matter what we did with the tire forces. These values will remain unchanged whether or not you had changed the adhesion value. Let's move on to our next collision speed of 10 miles per hour. And let's look at the updated result. Again, we go to the Auto EES object, which contains all of our collision data. And now we see a new value for object 2's post-impact speed, which is 5.442 miles per hour. And let's just go through the rest. I'll just go through the rest without talking. You get the point. Okay, there we have all of our data points from our series of tests. Let's go ahead and plot those values, and I'm willing to bet we're going to get a straight line pattern. There we see our straight line pattern. We have what looks like a strange outlier. I'm going to double check. Perhaps I mistyped. And it looks like I did mistype that value. All right, let's fix that value. Nobody's perfect. There we go. We fixed that outlier. And again, we have the closing speed on the x-axis. Maybe I'll put some axis titles for once. Closing speed that has units of miles per hour. And V to F, which also has units of miles per hour. Okay, let's do a linear regression fit. I'm going to set the intercept equal to 0 and look at the r squared. R squared is on the money. 1, perfect correlation, positive correlation, just like you would expect. And the slope is 0.544. Let's get that whiteboard. Let's return to what our equation was for the slope. We expected that the slope would be 1 plus epsilon over 2. And from our fit, that came out to be 0.544, which means the expected restitution based on the combined results. Using my calculator here, I'm cheating. Is 8.8%. So what happened? We expected that the restitution, coefficient of restitution, be something more like 10%, which is what's being used by the virtual crash collision model in this case. What we didn't take into account, and I sort of lied to you, is that there's some rotation that occurs during the impact. And we can get a better view of this if we go to our profile, view, and let's just slow the collision down. Let's actually look at a lower speed case. Let's watch what happens during the impact. We could see that the blue vehicle has some roll and the orange vehicle has some pitch just after the collision event. And what this means is that some of the initial kinetic energy goes into rotational energy for both vehicles and not 100% into translational kinetic energy post-impact. And if you're going to do a precision check that your simulator is doing the right thing, well, you should account for that effect. So let's go to a new whiteboard and see exactly what I'm talking about. We can't quite model this as one-dimensional collision of point masses. We actually have two extended objects, and we could say they're constrained to move along translationally along the x-axis still, but there's actually a rotational degree of freedom that we should kind of be careful about and account for. So here are two cars. Now I've upgraded from point objects to rectangular objects. Slight upgrade. And let's get my brush back. Here's vehicle 1, and it's moving here this way with the pre-impact speed of v1i. And of course vehicle 2 is at rest initially. And let's say the centers of gravity, these are identical vehicles, so the centers of gravity are at the same height. And we could look that up even in the trial version of the software. But just because the impulses are aligned along to run through the centers of gravity in the XY projection doesn't mean they're aligned in Z. I misled you intentionally for this problem. Actually, in the collision model, the Z position of the impulse, at least for these two vehicles, is below the centers of gravity. So here's our impulse on vehicle 1. And here's our impulse on vehicle 2, which is pointing in the opposite direction, equal magnitude opposite direction. And so we have a Z displacement from the point of contact and the center of gravity, and that's going to cause a net rotation. Our lever arm for the torque, let's call it R1, and here we have R2. That's just a distance in Z from the center of gravity to the line along which the impulse is acting. And that will obviously cause a rotation this way for vehicle 1 and this way for vehicle 2. And that is probably what we see if we look carefully. There we go. So the orange vehicle pitches with its nose down, and the blue vehicle rolls just as I've drawn it. And so we have to account for this effect. Now how do we do that? Well, this is when your pencil and paper calculation starts to become a little more complicated. But what has to be done is that we have to update our expression for delta V2, which we originally wrote as the closing speed times 1 plus epsilon all over simply 1 plus m2 over m1. Well, to account for rotational effects, the way we'd write it in this case is like so. Now we have to have some rotation terms. And of course the virtual crash system is doing this. We have to do it by hand, but virtual crash has these solutions programmed in, automatically accounting for these rotational effects. And again, R1 here is the Z distance from the line on which the impulse is running to the CG Z position, and the same for R2. The line on the distance from the Z distance from the line on which the impulse is running to the Z position of the CG of vehicle 2. Now, to make your lives a little more complicated, the moments of inertia here, I1 and I2, are going to be different moments of inertia. For vehicle 1, that moment of inertia is along the y-axis because it has to do with the pitch degree of freedom. And for I2, it's along the x-axis because this involves the roll degree of freedom. So we have to take care and make sure we account for that. So I propose we update our experiment. Let's assume we know what epsilon is, 10%. And now let's see if we can solve for what R1 and R2 are in this case. Now R1 and R2, I submit to you, are actually equal. Because the position of the impact on both vehicles is the same in Z, and the CG height is the same in Z. So R1 is going to equal R2. I1 will not equal I2. And so we need to do a little research to find out what those values are. How do we do that? You simply click on the vehicle or its label in the layers display, and then go to the mass properties, and you can see the vehicle mass, which is set in the trial version. Sorry, it's locked. Can't change it. And then you have the moments of inertia about the X, Y, and Z axes. These are the vehicle local frame axes. And what we want to do is note them and take the ratios of the masses and moments of inertia. And we need two ratios. We need M2 over I2. We want the moment of inertia about the x-axis. So now we have our two ratios. And we of course know M1 is equal to M2, so that ratio is simply 1. And now we just have a simple algebraic problem to solve. So I have my new whiteboard. And what we need to solve is the following equation. And we know that this expression is going to equal to our fit slope that we obtained before, since it's just delta V2, the ratio of delta V2 over V rel I. And now we just need to solve for R. If I could spell the word solve. Now I'll already tell you I calculated, while you weren't looking, I calculated what the sum is. And it comes out to be 0.325508. and that would have units of inverse feet squared. Our slope had a value of 0.544. 1 plus restitution is just 1.1. So we have 1.1 over 0.544, and that's equal to 2 plus 0.325508 times r. And that should be r squared. I just realized it. Nobody spoke up. That should be r squared. The reason I figured it out was because I saw my units in feet are inverse square, and r should ultimately have units of feet. Okay, so do a little algebra, and you'll find that r squared must equal to the ratio of 0.0220588 all over 0.325508, which is equal to 0.06776, and that implies, if you take the square root of both sides, that r is equal to 0.2602, I think that's good enough, 0.26 feet. And remember, this is equal to the distance between the z position of the center of gravity and the z position of the impulse, which is the impulse is basically aligned with the xy plane. So you could consider that to be a constant value. Okay, so that doesn't seem like such a large value, 3 inches or so. That 3 inches of offset in z is enough to cause the rotation. Let's see if that's consistent with what we see in the virtual crash simulation. What would this predict for the z position of the impulse? Can we see if that agrees? Well, first we need the z position of the centers of gravity, and we can find those by going to size. Pick a vehicle, doesn't matter, they're both the same, and go to size, and then you'll see CG height, and you could just read that off, 1.772 feet. And now all you gotta do is subtract 0.2603 from 1.772, and you will get that the z position of the impulse is going to be something like 1.5117 feet. That's from the xy plane. So let's check that this is consistent with what virtual crash is doing. First, let's make a box object. And I'm going to make it as high as the CG positions of both vehicles. And when you do that, you need to make sure that it's sitting on top of the XY plane. And that means that the Z position of the center of the box should be at half the height. So there we go, I've adjusted the position. Let's go back into that profile view, take a look at what's going on. Looking at the contours view allows us to see inside through the cars. So the upper red line right here corresponds to the upper surface of the box we just made, which should sit at the same height as the vehicle CGs. And just by picking the vehicle and looking at where the icons show up, the control icons will show up at the same height as the CG. So if you move the CG up and down, you'll see these icons go up and down. And sure enough, those icons sit right on top of the box that I made. Let's look at it on this guy. Let's stop the physics simulation, that might help. Okay, there's our CG height, and there's our box, and we can see that they're sitting on top of each other. As promised. Okay, well now we think we understand where the CG heights are. Let's now change the height of that box to sit at the same, so that its upper edge sits at the same z coordinate as our impulse vector. Again, you gotta change the height on the XY plane with respect to the XY plane. And we should see the impulse vector start, the point of contact should start at that height, I claim, at roughly a 0-degree angle with respect to the XY plane. Let's see if that's true. We could take a look at the vector. We see the impulse vectors pointing in equal and opposite directions. There's a little bit of a non-zero angle between the impulse vector and the XY plane, and that has to do with how the bounding boxes for the vehicles overlap. And there's the collision algorithm will set the angle of the normal axis dependent on how the bounding boxes for the vehicles overlap near the time of collision. It's close to zero, and you could see that our red line corresponding to the upper surface of the box, which is our prediction for the height of those impulse vectors at the point of contact, we could see that we're pretty much on the money. That using our estimates from our hand calculations, we were able to predict the position of where the impulses, the z position of the impulse vectors would lie at the point of contact for both vehicles. And don't forget, that was primarily driven by our fit that we did to all of our data points. And the fact that the r squared was equal to 1 tells you that these parameters right here, which are just purely a function of the moments of inertia and those the centroid of the impact impulses, that doesn't change from collision to collision that we simulated. So this term right here would remain the same whether we were colliding at 10, 20, 30, 40, or 50 mile per hour closing speeds. So this didn't change, which explains why our data points fit along such a nice tight line. So indeed, virtual crash is doing just as we expected. Going through this complex analysis, we were even able to predict where virtual crash placed the impulse vectors on each vehicle in Z pretty well. So there's no magic here. Virtual crash is doing what you expect. And you can see even with the trial version of the software, you can do some pretty sophisticated analyses. And I invite you to do so. Put it through its paces, make sure you're comfortable with what it can do, and purchase a full license and unlock the full potential of this pretty amazing software. Thanks for watching.